Hello, thank you. Sorry for the wait.
I think
Hello,
everyone's
good
here
afternoon.
now.
Thank you for having us at this conference. We are the Hyperlink braking team, and we will be presenting our presentation on eddy current braking. We will be covering what is eddy current braking, the types of brakes used, why we have chosen eddy current braking, and the additional benefits of using this type of technology for the braking application, and our conclusions. I'll be passing on to Aleph, who will be sharing with us what is eddy current braking.
So what is eddy current braking? An eddy current braking system is a combination of both Lenz's law and Faraday's law, I believe we all know. And to calculate the size of the induced EMF, we use Lenz's law. And from this equation, we can see that by both changing the magnetic flux all the time, we could change the size of the induced EMF. Other ways you could also maximize the eddy currents. We could increase the magnetic flux density. We could also use a conductor that has close to zero resistivity as possible. So on the top right hand side of the screen, you may be able to see a graph of different metals and the electrical resistivity of them. And for cost effective reasons, we will be using aluminium. And we could also increase the volume of conductive material passing through the magnetic field. So essentially what that does is we have more electrons that are able to form currents in the metal, and therefore that would increase the size of the eddy current, and therefore increasing the size of the induced EMF. We could also reduce any planar discontinuities such as cracks in the material. And on your right hand side of the screen now, the bottom picture, you could see that there is a complete metal sheet, and then there is metal slices. And when we do this pendulum experiment, we can see that the metal sheet stops a lot faster, and that means that this is because you can complete a full loop of current in that metal, whereas in the other stripes of metal you cannot complete loops as easily, and therefore we'd want to reduce cracks as much as possible. We could also decrease the time at which the conductive material passes through the magnetic fields. As I said before, the smaller the time and the faster the change in magnetic flux, that would increase the size of the induced EMF. Now I'll be passing it on to Kurti.
You're muted, Curdy.
Thank you. Thank you. Thank you, Aleph. There are two common types of eddy current brakes, circular and linear. Circular brakes can be designed two ways to induce eddy currents. It could be like figure 1, a stationary magnet which faces a rotating metal disc, which rotates and cuts the magnet's fields, or electromagnets along coils on a spinning wheel. This type of brake is widely used when an immediate braking force is required, such as for emergency situations, as the dynamic interplay between the stationary magnets and the rotating discs ensure a rapid or nearly instantaneous stop. Roller coasters are a good example of linear brakes, which use permanent magnets attached to the track and induces eddy currents in the metal parts of the roller coaster cars, coming to a quick but controlled stop. Permanent magnets are used as a safety precaution in case of a power shortage, ensuring that the car is able to come to a halt. Linear braking induces eddy currents, creating a magnetic field opposing motion, gradually slowing down the object. In conclusion, between choosing linear or circular brakes, we have chosen linear brakes as they ensure the pod to halt with precision and control. I'll be passing on to Matthew, who will be talking about why we choose eddy current braking.
Hello, my name is Matthew. So eddy current braking has many advantages in the design and manufacture of Hyperloop pods. Some of the main advantages include that, as shown in figure 1, It's a wear and abrasion-free braking mechanism since there's no pads that are used for eddy current braking technology. The conductive plate uses the interactive forces in the eddy current to oppose the field from the magnets, which creates a braking force. Figure 2 shows that the amount of power delivered in braking is proportional to the velocity that the pod is traveling in. A high velocity will therefore mean a high force exerted to slow down the pod. The system, however, does not rely on an external power source. Instead, they rely on induced currents in the conductor that are produced through the use of a permanent arrangement of magnets. And due to the strong direct interactions between the field and the opposing induced current, the strength of the electromagnets can be set at an optimal level to provide the desired braking power at a given velocity. So any adjustments made to the strength of the electromagnets gives a swift output with a minimal response and lag in the system. However, like all systems, eddy current brakings have a few considerations which need to be addressed, and one of which is a net zero relative velocity of the pod when there's a net zero braking force, which means that a secondary system will be needed to be implemented to bring the pod to a halt. For example, a mechanical braking system which will use pods, but this system will only be used occasionally whenever the pod is needed to be brought to a full stop. Due to the fact that there's a form of resistance that is formed when the induced eddy currents oppose the magnetic fields, resistive force is converted into unwanted forms of energy wasted in the system as heat. So this heat energy can be potentially dangerous for the pod, as it can cause serious damage to the mechanical and electrical subcomponents. I'll now pass over to Jamal, who's going to be speaking about why eddy current, the additional benefits of eddy current technology and applications.
Thank you, Matthew. So the additional benefits of using eddy current within braking application covers 5 areas, which are noise pollution, environmental impact, external mechanical impression, maintenance, and automation. These benefits are not only exclusive to a Hyperloop pod, they would be applicable to all eddy current braking systems. As the opposing magnetic field produced by eddy current is in effect, the rate of noise pollution is non-existent, as there is no contact between the two forces. The only cause of clatter would be taking place with the sudden change of direction from within the system. Due to the non-contact behavior of this braking system, the frictionless state produces up to no greenhouse gases when taking place, indirectly causing zero mechanical impact on the I-beam as well, which would be during the braking phase as presented in figure 1. This also emphasizes the maintainability aspect. It is true that this system requires low maintenance to keep running, as well as maintain due to the slow rate of wear on the magnet. Hence, the possibility of automation is very realistic when scaled up to the industrial standard. That would further take me to the conclusion of this presentation. It is clear that there is a future with this technology when scaled up to the intended market due to its impressive braking forces at high speeds and its reduced carbon footprint compared to the conventional methods. And therefore is the reason why we have decided to use eddy current system as our main braking source. Thank you for listening.
Thank you very much. Eddy current braking from Hyperlink, very, very interesting. Now it's the question period. We're still very ahead of time, so we can take our time with the questions. Does anybody want to post the question in the chat or raise their hand? I do have some questions, but I'll let the chance of the public first. Okay, well, I guess I'm gonna ask my questions.
Sorry, also, we forgot to mention,
Yeah.
our
ahead.
team head is not currently available. He had to take the time off because he had some, I think he had work to do, so he couldn't
No
be with
worries,
us
no
today. So
worries.
some of the questions that you may ask, we might have to rely them on to the team head, just in case.
No worries. I was just wondering, so you guys have an eddy current breaking? Are you guys designing that right now, or will that be like for a next year target or something?
So we already have a sample to work with, but we are currently building on it. So it's not up to date currently. We are currently working on it. But we are trying to improve it so that it is up to scale with our future plans with the HyperPod.
Also, it's meant to be in line with the propulsion team. So depending on how big they decide to make their propulsion system, we're going to have to align that up with our braking system. So a larger propulsion system means a higher amount of force needed for braking. So
Yeah.
a larger scaled up braking system.
Makes sense. What kind of simulation do you guys use? Or do you use a simulator, or like what? I mean, what software? I mean,
It's console multiphysics.
so okay.
Yeah.
I think we have a question from the chat. How do you plan on using guidance side of loops? Question from Marcel.
I don't exactly get what the question's asking.
Maybe Marcel, you can take the mic.
Sorry, yeah, from my understanding, or at least from the picture, the levitation, the guidance, and the braking is just one set of limb, or are they separate sets of limbs?
Yes, but fusion is weird.
Hi, sorry, if I could just answer that. I am the team captain of Hyperlink. My team is still pretty new with everything, so just to answer your question, it's not just one set, it's one set of a dual linear induction motor, and as we are still in the beginning phases of it, we're trying to kind of build the system in alliance with the braking system, and then as the years pass on, then we'll focus more onto like the guidance and the levitation bit. Hope that makes sense.
So how long did it take? Another question. How long did it take to run these EM sims, and what hardware were you using?
I think that's a question to be answered by our team head, as he was personally working on it last year.
EM is, I guess it's electrical mag.
Yeah, our main focus right now is on the eddy current, and I think since he was working on it last year, he would be able to answer that question. Sorry about that.
Okay, do we have an answer for Alex, or?
Again, I would be able to answer that. The EM sims themselves, it took us about 2 months to learn and run it completely on console, and the hardware, I don't particularly understand what you mean by hardware. We just use the normal laptop that we have, and we had the software in our own laptops.
How is eddy current braking system will heat up during braking? I don't know if you reached this level of analysis of heating up? Another question.
As an answer to Raphael's question, how eddy current braking causes heat up, it's there's a form of resistivity that is when the induced eddy currents oppose the magnetic fields from the permanent arrangement of magnets, the resistance is converted into additional energy, which is in the form of heat. So that's how heat energy is produced. It's the resistive energy from the interaction of magnetic force and the induced currents.
Just to add on what Matthew said, when the heat is produced by the eddy currents, as the pod will be in linear motion, it will dissipate rather quickly, due to the air being able to escape quite quickly. So, yeah.
Makes sense. Maybe use ANSYS and have, okay. Great. So I think that was all the questions. Thank you very much, Hyperlink. Thank you guys. It was very interesting
Thank you.
for eddy current braking, and hope to see you in the conference